carrier mobility, and a good carrier mobility, still Google will not be able to answer. And one of the reasons for that is that we have a limited information, I would say, about the material's properties. So if we look in encyclopedia about inorganic compounds, so there is 50,000 to 70,000 of those. And if you look at the number of available dielectric constant, there's about 300 to 400 of those for different compounds. You have the elastic constant, for 200 compounds, roughly. The band gaps for 200 compounds. And if you put everything together, basically, and you make a guess about how many materials you have. So here, even looking at 50 to 70,000 materials, when you look at the amount of information available about them, that's basically a coverage that is below 1% coverage. Okay, so basically, if this is a map of Louvain, where I am. And basically, if you had been here for the presentation, if you had something like 1% coverage, this is the map that you would have had, meaning that basically you would be lost. And in fact, as material scientists, when we have to design new materials, we often operate almost in the dark. We know very little about the materials in the end. So our experimentalist colleagues, usually what they do is that they proceed by trial and error. They test different materials. And for instance, Edison, when he had to choose the material that he put for the filament of the bulb lamp, he tested something like 3,000 materials, among which the heirs of his assistants. And in the end, the material that he got was not tungsten, which we used afterwards. So you see that this is very time consuming, and this is the kind of thing that we would like to avoid. In this framework, ab initio calculation have reached a level of maturity that is such that you can basically predict the properties of the materials even before they're synthesized. And so the codes that have been developed to do ab initio calculation and the amount of computer power that we have at the end now make the field mature enough to do what is called high throughput material screening. So typically what you want to do is that you take something like 1,000 or 100,000 of compounds and you compute different properties that are supposed to be at a given value in order to satisfy the requirement for a given application. As you see, most of the material, they don't satisfy all the criteria in terms of the different property. And so they end up here in this dumpster. Some of the materials, say typically 10 to 100 of those, meet all the property requirement. And so we can suggest them to our experimental colleague to synthesize them, make sure that it's the good material and to characterize it. And hopefully, if we did a good job in terms of the prediction that we made, then the material that they will have will meet the property requirement. And in principle, it would be faster to have developed such a material because this process of computing the property is actually faster than the trial and error process that I told you before. So in all this, here, this part that is to deal with thousands of compounds and compute their different properties, that's the realm of high throughput. And as you have seen, there's a lot of information that goes in the dumpster and actually it doesn't go in a dumpster. It goes into databases because we want to keep the information that we already have about those materials. So for some of them, we only computed one property. For some others, we computed two. And for even less, we computed the 5 properties that are here. And so that goes into a database in such a way that we can then do data mining. So let me give you an example of such a funnel here. In the case of an application, which is the need for materials that combine both transparency and conductivity. Such materials are needed in touch screens where you want to see what's coming from the screen, so it has to be transparent. But at the same time, when you touch your screen, you want something to happen, and so that needs to be conducting. In the same way, in a photovoltaic panel, what you want is that the upper layer here needs to be transparent because you want the light to go into the film, to go in the absorber, and in the absorber, it creates an electron hole pair And once the electron hole pair is created, you want the charge to separate, and then you want to collect one of the carriers here and the other one being collected at the back gate. And so this material, besides being transparent to let the light in, it needs to be conducting in order to collect the charges there. And having materials that are both transparent and conducting, that's kind of contradictory, because to be transparent, you need a large band gap, and to be conducting, you need a small one. And so typically the kind of funnel that I was showing you before with the calculation of different properties could be something like this here. So for such a material, you want it to be stable, you want to be transparent, you want it to be conducting, and you want to be dopable, as I will explain. And then finally, you will get some materials that are interesting for the purpose that we were discussing before. So you want it to be transparent. And so what you want is to have a wide bandgap material in such a way that the photons that are in the optical regime are not absorbed by this wide bandgap. You want it to be conducting, as we said, we want it to be transparent and conducting. So the conductivity can be measured by looking at the mobility of the carriers. It's actually proportional to the mobility, and the mobility itself is actually related to the inverse of the effective mass. So if you look at oxide, typically what you will see is this kind of band structure, meaning that you have a conduction band that is very dispersive, and as a result, the effective mass, which is inversely proportional to the second derivative of the energy as a function of the wave factor k here, you see that when you have a very dispersive band, you will have a low effective mass. And if you have a low effective mass, you're going to have a high mobility, and then you will have, with a huge probability, you will have a good conductivity. The only remaining thing is going to be the density of carrier, and that will bring us to the dopability afterwards. But so it's really important to have a good mobility here, and so you need to have a very dispersive band. The problem is that in many oxides, as you see, the valence band is not very dispersive. It's very flat, and this is due to the oxygen P character of that band, and that leads to a high effective mass, and so a poor mobility. And so in terms of transparent conducting materials, there's a difference between the p-type and the n-type. So the n-type are usually quite good with good mobilities here, and the p-type are usually quite bad. So typically a factor of 10 in terms of mobility compared to the n-types. And so the next step is indeed to dope the material, because, okay, as I said, once you have a wide band gap, it's not conducting. And to make it conducting, you want to dope slightly in such a way that you have enough carrier, be it electrons, like in the case of N doping, or holes, like in the case of P doping. So this is an example of the kind of funnel where you do a calculation for many, many materials. And as I was showing before, often some of the materials, maybe they meet 1, 2 criteria, not the third, sometimes not the fourth, sometimes not the second, and so on. And all those materials go into databases. And so there's been many examples of these kind of funnels for different properties, for different applications, and that for which different properties were computed. And as I said, many were thrown, but when they were thrown, they actually went into databases. And we have seen many high throughput calculation databases that have appeared online, and with a lot of data that you can have a look at. So there's a number here, and most of the people from these databases are going to give you a talk in the framework of this conference, where they will present their database, and then how you can query it in different ways, I would say. So when we look at the content of those databases, of course, the time that is needed to compute different properties varies quite a lot from one property to another. So typically, if you look at the structure of the material, its chemistry, the electronic structure, these are properties that are typically quite easy to compute within DFT without a too big computational time. If you go to different properties such as elasticity, piezoelectricity, you see that these are properties that are more complex to compute, and so the computational time is much bigger. So it's no surprise that when you look at the amount of data that is available in the different databases, most of the information is about the structure, the chemistry, the electronic properties, and a tiny fraction of the available information is about those more complex properties. And this is where big data can come into play, because typically you have not very much data there, but still you would like to do some kind of screening in the funnel that I was showing before that could be on elasticity and piezoelectricity, okay? So you want to have that, okay? So indeed, even the few data that you have here, you want to take advantage of that. And here, machine learning is really something that can help. So to try to extract an estimate of the properties for the elasticity and the piezoelectricity or other more complex properties by using the small amount of information already available in the databases. And indeed, our field is no exception compared to what we see in the rest of our lives. Big data is kind of revolutionizing things. So in our field, we started from learning through experiments, and we've seen this trial and error approach of the bulb lamp by Edison. Then there has been some work based on theory, because once you have laws, you can try to predict the properties of the materials. Even with just simple equation, you can make a guess about the property without the need to do a complex experiment to measure the property. Sometimes you need to go to more advanced calculation to make the prediction. That's the case of the computational science and DFT that's been used quite a lot. And now, thanks to all the data available, what we want is to be able to predict the property in advance. And the idea is that, as you have seen in the trial and error process, this is kind of slow, this is faster, but we want to be even faster in the screening process with some of the layers of the funnel that I was showing before that could be based on estimate of the property obtained through machine learning. And so one of the important tasks that we want to have is to be able to use all the information that's available in all those databases. And we would like to retrieve the data in such a way that you can machine learn the data in such a way that you can have a model that predicts, that is able to predict some properties, and then you can do the screening in a faster way. One of the difficulties is all these databases basically have their own way to be interrogated, so that they have what is called an API. The API is the way in which you make queries to the different databases. And each of them, till recently, had its specific API. And just to give you an example, if you take COD, the materials project Airflow, and you want to search for a simple material such as SiO2, the way in which you have to write the query is very different from one database to another. You see that here it's formula, and then you have to specify the formula. Here it's based, you have to define that before querying structure. Here it's still a different way of querying things.
عندكم إهمال. مين آخر كم مرة جلا؟ أنتوا رفعة. نفس إيش الغسيل، لو تغسلوا بتفضوا تخبوا عليه مية بتعملوا شيء. خلص شغلين بيرحموا.
I'm sorry. Okay, I muted the person. So if you take, if you're coming from the materials project, let's say that you're used to this syntax, and you want to use a similar syntax in Airflow, so you see you want to write SiO2, then this will return no response, because it's a completely different way to integrate things. If you're coming from, say, COD, and you're used to something like O2SI, and you want to use something similar in Airflow, say O2SI1, then this will return entries where the unit cell is SiO2, but it will not return Si2O4 or simulation that contain more formula units. So you see that it's very different. And the thing is that not only the way in which you query the databases is different, but the response they provide you is very different. Coming again to the example here of COD, when you write this formula here, what you will get is a web page with the link to the different COD IDs with the CIF file, which is very useful when you do a simple query. But if you want to do that with a machine, that's not very useful. And indeed, in that case, you want to specify the format to be JSON. And in that case, you get a JSON file with all the relevant information. Actually, you get also a JSON file because the materials project of A-flow as well. But the way in which these JSON file are structured is still different. In some cases, you have a first level where you have to click to see what's inside. In the end, each of the single elements are structures. And so, in the end, you have something that is similar. But even there, when you look at the details of each individual structure, the way in which it's formulated is still different. And as a result of that, a number of people from these different databases agreed to discuss about defining a common API in such a way that you can query all the databases with the same queries. And so we met during 5 years, basically, and we ended up with this API, a specification of the API, which is then common to all the different databases. And so with the same query, you can now interrogate the different databases. You see that you now have the same API for all of them, and we are now trying to push that to other databases. And this is really an important step into making the data interoperable in this case, so the, in the FAIR principle of findable, accessible, interoperable, and reusable also, because if you're interoperable, you can reuse the data in a different framework. Okay, I think that basically I've spoken enough for this presentation here. And so I will now give you the schedule of the 4 weeks of presentation that we have. So my first talk was here about this introduction to the Optimade API, and I will take some questions after I've finished. Then we will have a first demonstration of the Optimade Python tools by Matthew Evans. So that's a first way to interact with the databases through Python. And he will say also a few words about what is an API and stuff like that. Then we will have Marcus Skaten, who's going to speak about Nomad and how Optimade can be used with Nomad. And then you will see the different databases. So in 2 days, you will see Cormac Tor speaking about A-flow and Optimade. And I forgot to mention that, but at the end of our session today, we will give you a link to a number of exercises that we ask you to do all along the process of these sessions. And each Friday between 2 and 3 p.m. of your time, so that's CET +1, basically, we will have a question and answer session in which we will address the question that you may have in terms of the exercise, in terms of what you would like to do with the Optimade API, and so on and so forth. Okay, so that's going to be every Friday, basically. And then you have other talks about different databases. So there's one about OQMD on the 23rd, one about COD, TCOD on the 24th, again, the Friday Q&A session. Then you have one on the 2nd of December about the Materials Cloud, again, a Q&A session. Then one about the Materials Project on the 7th, one about HTTK on the 8th of December, and then one about MPDS, which is a commercial database, because we have also commercial databases that are involved in this Optimade project. And then the final session will take place on the 10th of December. And with that, I thank you very much for your attention, and I'm ready to take a few questions before ending to Matthew for the first presentation. Thank you very much. Questions about Optimade or about databases in general? I'll stop sharing my screen. Was all clear?
Yeah, thanks, Jan. I think from my side it was clear. So let's listen from other colleagues. Thanks a lot.
You're welcome.
Hello, Gian.
Yes.
Oh, can you please check your chat?
Oh, sorry.
The chat.
Yeah, I see. Sorry. So I see, please, could we record this? So we recorded that. like you use Abinit. Okay, I'm among the developers of Abinit, and so we've been doing some high-throughput calculation with Abinit indeed. So for instance, I was speaking about some complex properties. One of the workflows that we have is about phonon calculations. And so we did a computation of phonons with Abinit for about 1,500 materials. And as I was pointing, indeed, we used those 1,500 calculations to develop a machine learning algorithm, not to predict the phonon band structure, but to predict properties that are related to the density of states of phonons. This is an example. Did I miss another question in the chat? Other than that, I don't see any. Oh, someone needs my email.
Yeah, because I use Abinit too.
Mm-hmm.
So I need your mail. I want to.
Well, if you check my name on the internet, you will find my email without any problem.
Okay, thank you. Thank you.
Other questions about Optimade here?
Hello.
Okay. Yeah, sorry.
Yeah, so about, you mentioned just now when you presented that there are different formats depending on the databases. So now the format that will be given by the Optimade, is it going to be recognized automatically like by MatMiner if you are going to use it later for prediction? Or?
MatMiner basically wants to give it a CIF file. If you give a CIF file to MatMiner, that's perfect. And I think we can recover a CIF file from the Optimade API. And even if you don't have a CIF file, if it's a JSON, there's a way to convert the JSON to a CIF file, thanks to Pymagen, for instance, but there are other tools out there where you can convert things into something that is understandable by MatMiner.
Okay, thank you.
Yeah, there's going to be a presentation. So I showed you that one about the materials project on the 7th of December. It's going to be given by Jason Monroe, and I guess that he's going to give an example there. There's actually, as you will see, a way to use Optimade within Python. So there's the ways to make queries directly in Python thanks to that. And so you will see, and he probably will give an example there of how you can use that. Okay, is there other question? If not, maybe Matthew, you can start sharing your screen.
Hello, can you hear me okay?
Yeah, we can hear you.
Great, and you should be able to see my browser with...
It's probably the last slide, but
yeah,
this is the first one, yeah, indeed.
Okay. Great, okay.
We cannot hear you now, Matthew. We can hear some sound in your room, but not necessarily you. We cannot hear you. I cannot hear you. I'm going to mute some other people. But,
yeah, I've just switched microphone. You should be able to hear me now.
Yeah, now we can hear you.
So I think going into screen share muted my other microphone. So let me just find out a way to unmute that. Just so the sound comes off clearer in the recording. There's always something. Okay. So I'm just going to switch microphone again. So hopefully that's clearer now.
Yes.
Okay, great. I'm just going to keep an eye on whether it mutes again. when I click screen share. Okay, that should be fine.
Yes, we can hear you.
And I can see that it's still working. Okay, great. That's slide 2 already. Okay, let's try that again. So I assume the recording's already continuing, so I'll just start. So yeah, hi, my name's Matthew. I'm going to be sort of running some of the exercises over the next few weeks. And I just thought today I'd talk to you more about the sort of technical aspects of Optimade. So as Gian-Marco said, I will briefly mention Optimade Python tools and give a sort of quick demo, but it's mostly going to be talking about sort of what APIs actually are, and how we sort of came up with Optimade. So yeah, thank you very much for the invitation to speak here as well. Okay, so I mean, you've just heard from Gian-Marco sort of the broad strokes of why we came up with Optimade and what we can use it for, but sort of what it actually is physically and how it was constructed is sort of important in the process of how we actually came upon this thing. So I took this from our website, so it has to be true that the Open Databases Integration for Materials Design, which is what Optimade stands for. This consortium aims to make materials databases interoperational by developing a common REST API. So we're going to make sure we understand what REST API means. Hopefully you've already used materials databases and you can see why this would be a good idea. And then the exercise is going to sort of lead you through some examples of how you could use it in your research. So this came about from 5 annual meetings, as Gian-Marco has already mentioned, with about 50 or more than 50 authors. And the key is that we ended up writing about 20,000 words of, sort of plain text of English that a human should be able to read, that defines everything we expect from someone or from a database that implements the Optimade API. So it's quite a lot of work, for one, to agree on all those words. And it's sort of also the kind of thing that we don't actually expect anyone to read anymore. So the idea is that now we have these definitions in place, people can go away and write software tools that can already interpret this, and that the databases can also sort of, as long as they're the ones that have read the specification and can obey it, then the user shouldn't have to. And at the moment we have, I mean, this might now be out of date. I think we had about 15 registered providers. So these are sort of organizations or individuals that have agreed to host some number of Optimade databases. So it's quite a few people involved. And as of the last counts, there were more than 17 million crystal structures available within databases that use Optimade. So 17 million is the sort of the lower bound, because some databases don't allow people to sort of scrape them automatically. But this is sort of a conservative estimate, just based on the ones that we can query automatically. And I sort of have this kind of low resolution map here, just to show you where some of these databases are based. So I've added where I'm calling from in the UK, on the East Coast, just outside Cambridge. And I think this should be roughly where a lot of the people joining are. So my little database is called ODBX. And this is kind of how I got involved in Optimade as a PhD student, where we just had some data that we wanted to make publicly available. And it kind of made sense at the time that we would adopt this new standard and help develop it. But the main sort of players in this are sort of scattered around the globe. I mean, mostly in the Northern Hemisphere, unfortunately. It would be great to get sort of more contributors around the world. But these are probably the ones you've already heard of. So I mean, in North America, we have YokuMD, A-Flow Materials Project, where I think you'll have a talk about each of these. We also have Materials Cloud in Switzerland, Nomad based out, sort of fairly Europe-wide, but based out of Berlin, which you'll hear about today, the COD, and HTTK as well. And I think there's actually talks from all of these pictures I chose. That's why I chose them. And we recently published a paper on Optimade, so you can find some links to that at the end of my talk. But the key sort of table from the paper for me was this one, where essentially each column of this table represents the number of results that were returned for a given query using the Optimade format. So N1 here, if I remember correctly, we asked each database to give you every crystal structure that has the elements from group 5 in the periodic table, and this is the number they returned. So it can vary quite wildly. So as I say, my little toy database from my PhD only had 55 results. But then you look at something like Nomad, which had nearly 3.5 million results. and things like A-flow. And there's a lot of sort of information already in these numbers, in that you can see that Nomad probably includes data from other databases, which it does, and it actually includes crystal structures as individual calculations. So someone could run a calculation on graphites. If then another 100 people around the world ran a calculation on graphites, then that would add up to 100 in this number. Whereas the materials project, for example, do things a bit differently and have sort of one crystal structure for graphites, and then lots of calculations attached to that. So their number is much smaller, but in reality, they probably contain sort of similar information content to them. So don't sort of take these numbers as, oh, Nomad is very big, so it's the best. Sometimes smaller ones might be more sort of curated, but certainly if you want sort of all the information, then Nomad is going to be the one that contains the largest number of crystal structures, at least. And the key here is that, so the filter that we ran was exactly the same. So if you go to the paper, you can click on these numbers and it will actually sort of show you the results for each of these queries. And the only thing that changed, so sort of following from Gian-Marco's talk, the only thing that changed is the start of the URL that actually points to the database. And then these are two other queries that sort of narrow down the funnel a bit in the sort of the high throughput way that Gian-Marco was talking about. So I think the second query excluded anything that had lead in it. And the third query only queried structures that had 3 elements. Those two might be the other way around, but you can see there's ways of sort of narrowing down the data by using increasingly stricter filters. And here's just a list of some of the people involved in the paper. So this is the kind of 50+ people I mentioned from the workshops. So there's a reference to it in the Scientific Data Journal. There's also a link to the archive paper, which is maybe slightly nicer to read. Okay, so I sort of promised that I would define some of the jargon that we've already heard in my talk and in Gian-Marco's. So, sort of APIs generally, HTTP, REST, and then JSON API. So I'll just briefly do that. So, I mean, one definition you can use for an API. So when we say API, we mean an application programming interface. And it's essentially allows you to, there's a word missing there, but it should say allows your code to call someone else's code. Okay, so an API can just be a piece of software that exposes certain functions or methods, like a Python library, for example. It doesn't have to be anything to do with the web. And they're really useful for sort of defining, or for a developer to define the abstractions that they want their users to have available to them. So they aim to expose the actual functionality without needing the user to know about how these things are implemented. And an API specification, so sort of what Optimade is, it kind of defines this set of expectations or promises about what happens when you do the thing you're trying to do. So when you call a particular function, it tells you roughly what you should expect back. So if you make a filter, you should expect back either an empty list if there are no results, or a list of crystal structures if there are some results. And one example of this kind of abstraction, so you may have used some of these Python packages like scikit-learn. So scikit-learn itself uses NumPy for actually doing sort of array handling. And then NumPy is really just a sort of a wrapper over an even older library. So this thing called BLAS, which is written in a completely different programming language. It's almost incomprehensible if you actually try and read the code nowadays. But all of these sort of layers stack on top of each other until you have this kind of functionality of high-level Python library for machine learning, which of course then people go and build things on top of that. And it's all because each of these libraries have a well-defined API that sort of stays fairly constant over time and has these sort of expectations. So, when you call numpy.mapmul on 2 matrices, you're going to get a matrix back. And with any luck, it will be the result of actually multiplying the 2 you gave it. So web-based APIs are a bit different in that they actually let you run someone else's code, not on your computer, but on their computer. So anytime you're obviously on the web, there's just some computer somewhere in the world doing something as a result of your sort of keystrokes at your end. And that's exactly what Optimade is, really. So when you visit a particular Optimade URL, some electricity is being used somewhere else in the world to perform your query. Hopefully not very much electricity, of course. But that's the sort of the key to these web APIs. So these interfaces have to be sort of even more well-defined because you're interacting with remote systems and there can't be any sort of user intervention. So the person whose code you're calling on their computer probably doesn't know half the time, or at least they're not sort of watching you do it. So it's key that these things are well-defined. And there's lots of examples of these. So things like online payments or online banking. So OAuth, which is the way you can do things like log in via Facebook or via Google on some services that are sort of unrelated to Facebook or Google. Database queries generally. So often if you're running a database, it might be on a different machine to the one you're actually on. And sort of increasingly, this idea of offloading intensive operations to the cloud. So we're seeing things like sort of face recognition or translation. If that's, say, running on a mobile phone, then often what they're actually doing is pinging some server, nominally in California, that actually does the face recognition part on the images you send it. And there's actually sort of lots of security and privacy concerns there to worry about. But thankfully with Optimade, no one's sort of interested in the data that we really sort of pass around. So we don't have to worry about that. So web-based APIs are accessed through HTTP requests normally. And this is kind of just the backbone of, well, one of the backbones of the internet. And it's still a sort of a mystery to me how this stuff actually works. And actually works in terms of the fact it does work. So there's lots of complicated layers involved in this already, going from sort of physical cables up to advanced software to route the packages. But at its core, HTTP is pretty simple. It defines a set of methods. Again, maybe you could call it an API. These verbs, such as get, post, put, and delete, that a server can respond to. So this is basically just a server will be listening on a particular, listening in some way. We won't get into that. And if it receives some bytes that look in a particular way, like they start with get, then it should interpret the next part of the request as something it should maybe look up in a database or look up in its local file system. So I think I've got some examples further down. But these requests are the things that your browser makes essentially. And so if you've ever looked at like the developer tools in your browser, and when you access a website, you'll see loads and loads of requests, sort of GET requests typically, where it's doing things like loading fonts from external sources, or loading style sheets, or loading images from either sort of locally from its own file system or from some cache somewhere. So really, this is just sort of how the web works. But there are also other tools you can use on the command line, like curl or wget, and we'll see how as well you can do it from Python. So some examples, just very briefly. So a GET request for a company's logo on their website might look like something like this, where it starts with get. We want to get the image called logo.png from some path, and then this is just telling the browser or the server, sorry, that we're using some particular version of HTTP for that. Then a post. I hope this isn't going to go one at a time. I think it will. Okay. So a post is how you sort of give data to the server. So you say you're going to post to a particular URL on the server, again with HTTP 1.1.
Sorry, miss, can I interrupt?
Yeah.
Okay. So on this example, so you like telling to get the log from the certain website and with the HTTP address, right?
Yes. So there could be a longer URL at the front here.
Yes, of course. So, but you need to know that whether they have HTTP or whatever. And the 1.1 is the final address or what?
So yeah, that's not very clear. So 1.1 is the version of HTTP. So there's now also an HTTP 2, which is slightly different. So I only added that sort of for completeness, really.
Yes, I know this.
Part is just to get the URL, and then you're just telling the server what particular version to respond with.
And then once you get it, you post it again to the URL.
So the
post.
So you don't need to post anything back. So the post is kind of a separate example here. So the post could be used for something like a login form, for example, or if you're filling in your details to some company or some service. So if I quickly run through this, you'll see that we're posting something to some path test for the website here called foo.example. I don't know why I use that one. we're telling it what content we're posting. So here, this is some awkward way of saying a web form with some particular encoding. We're telling it how long the form is going to be. And then this is the actual data we're telling them. So field 1 here could be username, and then value would be your username. Field 2 could be your password. Hopefully they don't actually do it this way. But this is how you would send data to the server, and it can do whatever it wants with that data at that point. So you're expecting that, you know, with this simple, you know, a simple API for what test is actually doing. If this said like login, for example, then you know that in the background the server is actually doing something complicated, like it's looking at your encrypted password and it's checking it against this database of users, and then it might return with a, you know, sorry, you're not logged in, or it might keep you logged in for the rest of the session. So it can kind of do anything complicated in the background based on the request you have here. But at its heart, that your browser only needs to know how to do this kind of post part. So these are the kind of the smallest building blocks.
Okay.
But this is kind of background, right? So hopefully you won't have to actually do anything with sort of raw HTTP requests, because you'll be using a tool like the browser or like curl or wget that will sort of do that part for you. But I think this is useful to know what's going on in the background. Okay, does that answer your question?
Yeah, thanks.
So that's kind of all I was going to say about that anyway. So if we move on to REST, hopefully that font is legible. I'm sorry that's a bit dark on a dark background. But this says REST APIs, and that sort of stands for this representational state transfer. And you'll hear about REST APIs, I think, quite a lot in the field of material science. I'm not sure people necessarily know what it means when they use it, but it's just this idea that a web API can be stateless. And often these REST APIs will be used to manipulate resources on a server. So like things like database lookups. And by stateless, we just mean that when you perform a query, it shouldn't matter about all the other queries that have gone on before you. And any URL should essentially do the same thing, independent of what URLs you visited before. Unlike something like, well, let's say Facebook, where the going to facebook.com depends on whether you're logged in or not. There shouldn't be anything sort of going on there with a REST API, or at least, you know, you can log in through other methods. So, and yeah, so these don't necessarily have to serve this kind of resource approach, but in the case of Optimade, it does. And the resources we serve are normally crystal structures, but also things like references to papers and so on, as we'll see. So Optimade itself is based on a specific sort of flavor of REST API called JSON API. So we kind of adopt another standard as well. You shouldn't have to worry about that too much, but the idea is that there are other things that also follow JSON API. So if you know about Optimade, you probably also automatically know about these other packages, hopefully. And we write our schemas in a particular way that's machine readable. Again, shouldn't have to worry about that. But it's nice if you can sort of auto-generate tools and things. Sorry, I'm losing my voice here a bit. So if some words get lost, or if I'm not making sense, just ask me to repeat myself. Okay, so Optimade 1.0, we released it in July 2020. And when I say 1.0, I mean, you know, this is some set of agreed words. This is the 20,000 words. It's already sort of changed a bit since then. We've released 1.1 by now. But 1.0 had all these core features in it. So as we've said, it's a REST API specification for common access to crystal structure databases. So hopefully this idea of a REST API now makes sense. And by common access, we mean that the filters all do the same thing across different databases. They're kind of transferable. And also the responses, as we'll see, should also be of the same format. So you don't have to know all the different conversions between databases. As I've just said, this was the 20,000 word specification based on JSON API with these machine readable schemas. And this is sort of just a summary still, but it enables this unified access to 17 million crystal structures at the moment. And actually, importantly, we'll talk a little bit about this, that we have the ability to discover new databases that host Optimade APIs. And we have this, what's called a federated providers list, where anyone who has a URL that somehow is serving Optimade, they can just give us that URL and some extra information, and they automatically become a database provider. So there's no sort of barrier to entry. Even if you're just hosting a few crystal structures like me, that can be useful. and you'll sort of automatically be on them the same level as these bigger providers when a client queries you. And we also have some ways of sort of validating that the people that say they're hosting Optimade APIs are actually hosting sort of valid APIs. So hopefully the responses you get should be fairly consistent across different databases. So some of the features, I think I've spoken about this already, but we have these resource types for crystal structures and references. We have this sort of fairly well-defined grammar and filter language that you'll be using in the exercises. We also have this, what we call an introspective info endpoint, which allows you to ask the database what it actually serves without doing like full queries. We'll show you that as well. And slightly more boring version negotiation, and this sort of strict response format that allows the user to sort of know exactly what's being returned to it, or to them, sorry. But also the models themselves can be quite flexible. So if a database is missing a piece of data, there's sort of clear ways of saying that without it being sort of too difficult to implement. Okay, so we've mentioned this response format a few times now. What actually is it? It follows JSON API, as I've said, but that doesn't really mean a lot. And we sort of only chose this because it solves a lot of arguments very quickly, right? So if we just agree on a rough format, we then don't have to spend all of our time agreeing on JSON stuff. We can actually talk about Optimade stuff. And I should have probably defined JSON here. So JSON just stands for JavaScript object notation, which is not particularly useful if you don't know what it is. But if you're familiar with Python, then JSON looks almost exactly the same as a Python dictionary. And again, I think that will become clear when we actually look at some examples. It's just a set of sort of key value pairs, and the values can be also be dictionaries, or they can also be arrays or lists and things like this. So hopefully that will be clear soon. But every response in Optimade has these keys, data, links included, and meta, and they all have sort of definitions of what can be under those keys. So every member of the data response is further broken down into a type, an ID, then attributes and relationships. So again, as we'll see, so a type will normally be structures for a crystal structure. The ID will be kind of like the unique ID for a particular material or structure, similar to like an ICSD ID or materials project ID you might be familiar with. And then attributes is this sort of sub-dictionary, this big dictionary of the actual data corresponding to the crystal structure. So this could be things like chemical formula, it could be positions, it could be lattice vectors. And then finally, relationships, you might not see very much, but this is how you can say that another entry or another external URL is somehow linked to this structure. So you could say that one structure has a relationship with a bibliographic reference, so maybe the paper that the structure was published in. So there's a mechanism for doing that as well. So we don't actually, as I say, we don't actually have that many data types in Optimade at the moment. It's just structures and references. And the key thing is there aren't really any, I've called it attached semantics to this. So a structure doesn't mean a stable crystal structure. It doesn't mean a structure that's been made in the lab and then sort of characterized with diffraction or something. It could mean both of those things, but really it just means a valid arrangement of atoms in 3D space. It doesn't even have to be periodic. Well, it doesn't even have to be 3D actually. It could be like a molecule, or in 2D, it could be a sheet. So the idea is that it's, that's a bigger question of how we sort of add semantics to these things. But we're simply defining a data representation, and then each database can interpret or can serve what it wants as a structure, which is, I think, maybe one of the confusions of Optimade at the moment, which the exercises, again, will hopefully guide you through. So structures simply serves this crystal structure type, and perhaps surprisingly, it only has one required field, which is this sort of obscure thing called structure features, which is kind of just a tag that's used in Optimade. But the idea is that some databases don't have positions because maybe they don't have all the positions because they're from an experimental diffraction pattern and they know there are missing hydrogen atoms, say, so they actually can't serve these positions. Or perhaps they're actually storing in their database a reduced representation of the crystal structure, and you'll need all the symmetries to be able to actually unfold all the positions. So there's lots of examples where it doesn't make sense for a database to host that data. So Optimade has tried to be quite flexible to that. But what you should find is that almost every database has all of the other sort of recommended fields. So things like chemical formula, things like the number of elements, as we'll see, should be fairly common across all of them. So yeah, that's just what I've said, that these sort of should level fields. And then references just follows, if you've used LaTeX, just follows the kind of similar fields that you get in a bib file. So authors, journals, titles, things like that. But you can basically put anything there. Okay, the right-hand side has appeared first, so I'll go for that first. So filtering in Optimade uses this custom grammar. There are lots of examples in the specification, also in the paper I mentioned earlier, and in the exercises. It should be, I think the grammar itself is fairly clear, but sometimes if you're using particular tools, it can be a bit tricky to use. So this idea that you need to encode or URL encode the filters for some tools, we'll talk about briefly. But this just means things like, a URL technically can't include spaces and quotes mean a certain thing. Often your browser, for example, won't care and it'll do that conversion for you. But if you're using something like a command line tool like curl, for example, you might not get the results you expect. So we'll briefly touch on that. But these filters should be transferable between databases. And hopefully, as we sort of develop Optimade more, these will become more powerful. And then what I wanted to say first is that each entry type can be filtered at all, and at these entry listing endpoints. So for a single entry, you go to, as you'll see in a second, you go to an Optimade URL / the entry type you're looking for. So normally structures / and then a particular ID, and that will just give you one entry back. For example, if you want structure 12345 from somewhere, you could visit this URL with the database URL at the front. For multiple entries, so you could just leave it as /structures here without a filter, and then you'll just get everything from the database back. But often you actually want to add a filter as well. And in fact, some databases, if you ask for everything, will actually end up giving you nothing because they're stingy and don't want to waste their compute time, I guess. So for example, this is probably the first filter you might have seen. So you would have the database URL at the front here, /structures as the entry type, and then !, filter equals n elements equals 2, which means you're going to be querying that database for every binary crystal structure that they have. Okay, so my animations are slightly messed up here, I'm afraid, but we'll start on the right again. So this is a very minor point that there are these things called index metadatabases to worry about. Well, hopefully to not worry about very much, actually. And the idea here is that one provider can serve multiple databases, and the index just provides a way for the provider to list the databases they serve. And this is the link you would provide to join the sort of Optimade federation. So you just say, I am a provider, and the list of databases I serve can be found at this point. So then you can sort of dynamically change the databases you serve, but the index sort of stays fixed. That's a minor thing. More importantly, I just wanted to talk through the links endpoints, where you can link to sort of arbitrary resources. So this can be useful if you're using Optimade for the filter, but then want to go to, for example, the Nice Materials Project webpage for a structure. They should be able to provide a link to that directly. Or in the case of the COD, you might want to get the CIF file. They can also provide a link to download the CIF file directly in this sort of links endpoint. The info endpoint I mentioned briefly already, but this is this idea that you can get some provider-specific metadata and their sort of contact details if you have any questions about their database. And this is also used when if a database serves more properties than just the ones we've standardized in Optimade, they can list these here, give you a description of the property and whether you can sort of filter on it, which can be very useful. So yeah, this is this idea that you can extend Optimade without having consensus, as long as you do it sort of for a particular database. And again, I think we'll go through some of that in the exercises. And then versions you don't really need to worry about. It's just telling you which Optimade version each database uses. At the moment, they're probably all going to be using version 1. Okay, so that was a lot of talking. And I'm sorry if that was maybe too much information at once, but I thought it would make sense to do a very quick live demo, just actually accessing some Optimade APIs, the kind of stuff you might be doing either on Friday or whenever you're interested, to just explore what we actually have in Optimade. So I'm hoping this will also come up in the recording, but just in case it doesn't, what I'm going to do is first go and find the list of all available Optimade APIs. And then I'm just going to have a look at some of them in the browser. And then if we have time as well from the command line and maybe from Python as well. So I guess, I see the time is now 9:33. I've probably got about 4 or 5 more slides after this. So I guess Gian-Marco just stop me if I'm overrunning, but I was planning on going till about 10, I guess, if that's okay.
Yeah, that's perfectly okay.
Okay, great. So let's see what happens here. So the next slide as well, I'll just put up. This is going to show you some of the links that I'm going to go to. So you can sort of follow this as well if you want, if you're watching the recording or something. Okay, so let's end the presentation for a second. And let's do this all in a new window. So the one problem here is I can't zoom in on my address bar. So you'll have to sort of believe me when I'm typing stuff in. So the first thing I'm going to go to is the dashboard. Actually, the first thing I'll go to is the homepage. So please shout if this isn't readable. But I've gone to optimade.org essentially. Have a look around. There's some useful information there. One thing is if you're interested in getting involved and helping develop Optimade, there's some info at the bottom of the page. And also here's
Hello, Martin.
Hi there, yeah.
Yeah, the font is small.
Okay, I worry if I zoom in, it's going to become really thin in the middle. It should only be for this website. Hopefully it'll be bigger in a second, if that's okay. But you can go to optimade.org yourself and have a look at what I'm looking at as well.
Okay.
There's just some useful links there. And the only one I'm going to click on is this provider's dashboard, which should be slightly more readable. I wonder as well, actually, if
It's okay like this.
Let me reshare just this window, and then I can make the window thinner, which should make it bigger. I don't know if that's made any difference at all. But okay, if that's readable, that's fine.
Yeah, we can see it like this.
Great, okay, thank you.
Yeah.
So on this dashboard, so I'm now at optimade.org/providers-dashboard. I said the links are available in the slide. This just gives you it's an automatically generated list of all the providers. So you'll see there are 18 providers. There's 18 known providers and 18 of them are available, which is good. And there are 22 available subdatabases from those providers. And I recently added this sort of count structures. So it's like a sort of vanity badge, I guess. So this number's actually gone up since I did it, I think. So there's now 17.6465, I guess, million structures available within Optimade. And as I say, that's excluding some actual bigger databases that don't want to be scraped automatically, which we'll see in a second. So let's choose an example. I'm going to scroll down to my database because I know it's up right now. So ODBX, Open Database of Extals, Crystals. And when I click on this provider, it's going to give me some extra information. So you'll see that the database is served by this provider. I only have one. It's got the same name as the overall provider, so it's called ODBX. And this might be useful to maybe sort of advanced users, that we automatically validate, as I say, these Optimade APIs, and you'll get the list of errors that came up from validation for each database. So in my case, I need to fix the fact that ODBX DFT parameters field, so a custom field that's just available in ODBX, the field type wasn't properly reported. So that's something I, as the developer of that database, need to go and fix, but it's something that you as the user might want to know about if, for example, you want to try and query on this field. Okay, so this is where I've now found a database. Should we actually try and go to it now? So I can click on, hopefully on this link, and it will open the sort of landing page. And so I thought I'd go through some of the pitfalls that I fall into when I'm trying to query Optimade. So one thing is that the link you get here, so this is what we're going to call the base URL for the implementation. So this is optimade.odbx.science is the link it's going to go to. And there's actually no standardization of that URL at all. So people can serve whatever they want at that base URL. So some people have like a nice landing page like this, but other ones might give you like a 404 error that the page is missing. I might try and find an example of that in a minute. So don't be sort of put off by that. The key thing is that you should always have this endpoint info available to you. So whatever URL you get from the dashboard, if you add /v1/info to the end of it, you should always get like a JSON response if the server is up. So again, let's just zoom this a little bit. Okay, so hopefully again, this is readable. So what's actually happened here is that my browser has made this request. It's made a GET request to optimade.odbx.science for the v1/info endpoints, and I've been given back some JSON. So this is how my browser is interpreting the response. If you did this in Chrome, for example, I think by default you just get like a plain text response, but Firefox will let you sort of actually manipulate the JSON and have a look at it. So here are the two keys available from the info endpoint. Let's quickly look at meta first. So this is giving you some information about the provider and the query you made. So just things like we have a timestamp of when I made the query. It's telling me what database I'm querying, or what provider I'm querying, and some useful links there. So not particularly interesting in this case. But the data of this response. So as I say, we always have this ID, type, and attributes. The type here is info, so we're just going to get some information back. And we're told that what version of Optimade this database is using. We're told what versions are available. We're told the formats they're using and which entry types this database can serve. So not particularly interesting as a starting point. But if we now add /structures to the end of that URL, so we're now at v1/info/structures, or will be in a second. And the reason I knew that was possible is because we're told that available endpoints has this structures thing in it, which means that if we add /whatever they put here to the end of the info, we should get more info about that particular endpoint. So that's one thing that Optimade sort of standardizes. Okay, so let's quickly collapse the response again. The meta should stay basically the same because we're on the same database and we're doing the same kind of query. But now the data looks completely different. So we have these keys: formats, description, properties, output fields. Formats is just going to say JSON, pretty boring. But properties is the key part here. So this now lists every available sort of field in the Optimade API for this particular database. And any of them are sort of all the ones at the top here, so the ones that don't start with _ODBX, these are ones that are standard within the Optimade specification. So I've already mentioned ID and type as the way to give the ID and the type. And you'll see there's a full description taken from the specification there. It doesn't look particularly nice when you read it like this, but there's sort of nicer documentation for that as well. But the important thing is things like chemical formula, things you might actually want to query on, where we're told that the reduced chemical formula for a structure is a string, or as a string, sorry, with elements and integer chemical proportion numbers. So this is something you could then go and look up in the specification. And I've just sort of copied the definition there for my database. So that's all very well and good. We could then look at the particular fields that my database is serving independently. So something like the lattice vectors ABC rather than the lattice parameters as sort of ABC, alpha, beta, gamma, rather than lattice vectors. And the description here is just that you get the lattice parameters in angstrom and degrees. So these things might be useful if you're looking at response and trying to understand what these fields mean. So let's actually look at some structures now. So I'm going to delete the info part, and we're now just going to optimade.odbx.science/v1/structures. And now we're getting sort of a lot more data back. So let's just collapse one more time. So meta this time now contains some useful information about the structures or about the query. So we're now also told that the number of structures returned was 56. And we're told that the actual number available is also 56. So we've been given everything in one response. And the query is just, at the moment, it's just blank. So it's just /structures with no extra filter, which means we're sort of querying for everything. So if we now look at the actual data, you'll see that we have a list. And just to look at the first entry, so the ID is ODBX/1, so it's the first entry in the database. The type is structures, as we'd expect, because we're querying the structures endpoint. And then here's the actual crystal structure data. Okay, so this one's kind of a boring structure. It's just lithium, so it's just bulk elemental lithium with one element. The list of elements is just lithium, and the element ratios are 1 because it's one element. So very exciting, this one. I think I'll just very quickly talk you through the fields so you've seen them. Maybe on a different example though, that isn't just lithium. So hopefully number 2 is more exciting. There we go. So here we now have lithium 2 tin, so Li2SN. So all the fields we have, as well as an ID, we have this immutable ID, which is something that shouldn't change across different versions of the database as well. So you should always be able to look up this ID for this particular structure. We're given the time the structure was last modified. So in this case, it was, make sure I get the date format correctly. That should be October last year, 2nd of October. The elements this time, so we're told that it contains both lithium and tin, 2 elements, makes sense for the n elements field. Now we can already see that the formula is Li2SN, so the ratios should make sense with that, and they do. So we know we have, essentially 2/3 lithium and 1/3 tin. I wonder if that shouldn't actually round to a 7 there to make it add up properly. That's a different issue, I guess. Then we have these 4 different chemical formula to explain. So we have a descriptive formula, which can basically be anything the database thinks is useful as a description. So for example, you could have the kind of human readable formula, like something that includes oxidation states or charges or number of hydrated water molecules or something. Basically anything could be put here that can make sense to the user. But chemical formula reduced is a very sort of specific format where you have to have element symbols in alphabetical order followed by the number in each, or the proportion number in each structure. So this is the kind of thing you would actually filter on that should be the same across all databases. And this is also the example that Gian-Marco used, right? So instead of saying SiO2 or O2Si, it's fixed, or sorry, O2Si1, it's fixed that you have the elements in alphabetical order and you should exclude the 1. So here we have Li2SN, or it could be O2Si in the other example. The Hill formula is another way of representing this that you don't need to worry about too much. It's a different ordering where basically carbon and hydrogen get given priority. So useful for things like organic molecules or crystals. And then the anonymous chemical formula is a useful one because all it does is takes the first element and replaces it with an A, and the second element and replaces it with a B, provided, okay, slight caveat, the order has to be in order of chemical proportion here. So it's not in alphabetical order, it just happens to be in this case. And the key there is that you could search for things like, let's say you wanted all, ABX3 perovskites, say, you could search for that across lots of different chemical elements. So you could search for, I think in that case, it would be A3BC would be the anonymous chemical formula, to make sure you get everything that has one element with a proportion of 3 and then 2 other elements with a proportion of 1. And we'll see some more examples of that as well in the exercises. Dimension types, just telling you which, if there are any non-periodic dimensions. So you'll see the next field is n-periodic dimensions of 3. So in this case, we don't have any non-periodic dimensions. But if you had maybe like a slab, this would be 2, and then you could specify which direction the structure isn't periodic in here by replacing a 1 with a 0. And then some sort of more self-explanatory ones, things like lattice vectors, you just get the 3x3 matrix back. And the Cartesian site positions, you just get a list of 3 vectors for each position. Number of sites in this structure was 6, so you should get 6 positions back. Number of the species involved, so you can give some more information about what lithium is. potentially like the mass that was used in the calculation, the concentration of it. And this is useful if you have sort of different partial occupancy crystals, which is maybe sort of an extension we won't go into now. And then the last few telling you which elements are actually, or which species are actually at the sites that we get the positions for up above. And assemblies, you don't really need to worry about, no one's using it. Structure features is the one I mentioned before, where you can say things like, this is a disordered structure, so that people can filter out things that aren't ordered. So that was, yeah, I thought that would just make sense to run through the fields we actually have in Optimade, so you've seen them at least once before you dive in. Hopefully that was useful. So in the second part of this demo, I just want to quickly add a filter to this to show you how to do it. So at the end of the URL, I'm going to add filter, so question mark, filter equals, and then let's just do elements has lithium. And I'm not caring about putting spaces or anything in the URL. I know my browser is going to sort that out for me. So we execute that query. It goes to my database, actually performs the query. The meta information we get this time tells us that the filter we ran was elements has lithium, with all these extra weird percent encodings, it's called, for spaces and quotes. So this is the thing I was telling you to sort of, if you're using a more simple tool like curl, for example, you might have to worry about doing this part yourself, but we'll come on to that. And now we should hopefully see, well, in fact, sorry, let me change my query to elements has tin, because then we'll hopefully see that the first structure was ruled out. So instead of it being ODBX1 at the top now, which had just lithium in it, that's now been removed by the filter, and the first result is now ODBX2, which is the one with tin. And just to check the meta again, we now have one fewer result. So for my database, it's a bit of a boring query, but 55 structures are returned rather than 56, essentially. So we filtered out the one available. Sorry, the one only lithium structure available. Okay, so just to then show that these filters are transferable, what I'm going to do now is remove the start of the URL. So I'm going to delete optimade.odbx.science and replace it with optimade.materialsproject.org. So a completely different server. So, mine was running in Cambridge somewhere. This instead is going to, well, it might ping a server in America. More likely they have some fancy way of distributing their hosting, and it could ping sort of the nearest server to me. With this particular query that the elements has tin, and hopefully if I execute it, it looks like it's worked. So I get a completely different set of structures here. And because it's the materials project, they have, or at least they would claim to have, sort of all known materials plus more. So the first result this time is some magnesium tin phase. If we look at how many responses there were, so this time there's 5,400-ish responses to this query, which is a bit more than what I had. And we're told that in total they have 139,000 results. So let's just pick another random one. So this particular phase is selenium stannide, I guess, so SESN. And you'll see that all the fields I've just talked you through are the same. So the elements make sense, the element ratios make sense, the positions are returned in exactly the same format, and so on. So I could keep going through and changing this URL to every database or every different database, and hopefully they should all work. I'm not going to do that now, but maybe that's a useful exercise just to have a play around with it. And then also just to finish off, you'll see that I can also go to the info endpoint for materials project and get a similar result where I'm told some useful links about the materials project. Okay, I think that's all I wanted to demo for now. I won't go into the Python stuff just yet. Where has my presentation gone? There it is. Although that is just a ghost of the presentation. I need to find the actual browser window. There it is. Okay. So I'm afraid I'm doing a lot of talking for now, but hopefully that was a useful demo. And here's basically just the links I just visited if you wanted to go through that on your own. So homepage, dashboard, and then we went to the info for my database. We then went to the structures. We then added a filter to it. And then this is just the final URL I went to where I replaced the odbx.science with the materials project URL and did the same filter. Okay, I've already talked through a lot of these common pitfalls, so I won't dwell on this too much. But one thing is, as I say, that the database or the base URL that's provided in the dashboard often doesn't serve anything useful. So do remember to add an endpoint to the end of it if you're getting like an error message there. I do that all the time and confuse myself for a few minutes. Another one is visiting the wrong base URL. So you might end up at the one for indexing instead. Slightly trickier, but for this one, either make sure you're going to the right URL, and failing that, you can try also adding endpoints to the index URL. So for example, v1/links will give you the list of databases served by that provider. But basically, if you think a URL should be working and it doesn't, and you've clicked on it from somewhere, chances are you're either looking at either a base URL that doesn't serve anything or an index URL. So sort of don't panic and just try and go to the actual URL you wanted to go to after that and try and do your filter. And then the final pitfall is this URL encoding. If you're using a simple tool, you might need to escape, it's called, or properly encode quotes and spaces in your URL. And there's, for example, you can do this in Python with this standard library URL lib.parse.quote thing, or just use a tool that does that for you. So Optimade Python tools is the sort of Python package I've worked on mostly, and it's primarily for people hosting Optimade databases, but it might also be useful for people using clients. So, I mean, Gian-Marco said I was going to give a tutorial on this. I don't think I'll give a tutorial on this really. There's documentation online for this. But if you are interested, for example, at the end of this, in hosting your own data on Optimade, then we should definitely talk, and I can give you more info. But the documentation is all online for this package, and it's actually used by some of the clients as well that you'll be using in the exercises. So even if you don't think you're using it in the Python, you might already be under the hood somewhere. So I'll sort of rush through this quickly. That it should allow you to easily host a database if you already have like a server and all the complications involved with that. Perhaps the most useful part for a user is that it allows you to map to things like the ASE or PyMatGen formats. But you'll already see that you can also use PyMatGen directly with Optimade. But I guess the key is that this is used to actually host some of these databases. So it's used by Materials Project, Nomad, ODBX, 2D Mappedia, and the Materials Cloud. So again, even if you're not using it locally on your computer, you're calling Optimade Python tools code on someone else's computer as a web API. And it also provides some of these tools with validation, which you shouldn't need to worry about. Oops. This was just a brief picture of showing how an Optimade query actually works, which I don't think I'll go through, but it's in the slide if you want it. So basically here's a breakdown of the URL. Where does that URL go? What does the server do with it? How does it actually query a database with that? So if you're interested in that, you can find this in the slides. And then I just had some extra info about ODBX, which I won't go through, given that I've given you the sort of demo for it, just explaining what it actually is. This is kind of a very specific example. I think the other Optimade databases you'll see this week or in the coming weeks are going to be more useful for you. But there is some example code of how to write an Optimade implementation at this GitHub repository. So if you're interested, you can take a look at that. So just to sort of wrap up, so Optimade isn't sort of finished by any means. We've released a version 1 to actually get people to start using it. But we would like to add more features to it. And the reason I say this is just so that we would love your feedback as users of Optimade over the next weeks. So some of the stuff we have planned for sort of the next version would be more property standardization, handling things like molecular dynamics trajectories, if that's your field, and ways to agree on other definitions like DFT parameters, I think could be useful. We're hopefully going to be sort of constantly improving the tools we have, so better clients, easier ways to host your own data with Optimade, if that interests you. And then we have this vague idea of semantic interoperability as well. So going beyond just the format being interoperable, we would like the definitions themselves to be interoperable. And this is kind of a work in progress. And there's a couple of links to sort of papers and workshops there where those discussions have happened. Okay, so the exercises, Gian-Marco's already mentioned them. They are in a GitHub repository. I might just click on this link in a second and show you them. I think Gian-Marco said all this, that hopefully these times are correct, that it should be every Friday at 2 o'clock in your time. In terms of questions and things outside of those hours, there's this forum on matsci.org/c/Optimade. Feel free to sort of just start any kind of discussion you want there, or I think you can probably also email us if you can get our details. But for the exercise, I just want to stress that, please give us feedback on what you think is useful and what isn't useful. If there's something you're already stuck on, then don't sort of just keep banging your head against it. Either ask us, or maybe we can change the exercise to be more helpful. I think that the exercises at the moment are quite open-ended as well. So, don't feel like you're doing something wrong. Just sort of try it and play around with it. I would hope we're going to add a couple more exercises throughout the sort of month or so we have. So if you have any suggestions for what could be a good exercise as well, please do get in touch. And just to quickly go on the exercises in case you're not familiar with GitHub. So the link you get will just be to this website, and essentially all the exercises are available in this kind of README. So in the first page, so there's some intro, then there's some sort of text guiding you through each exercise. And just recently at the bottom, I've also added some example code for doing this in Python in kind of a manual way. But you'll also see some talks from people who have provided clients, which you can find links to in the introduction. And if you are familiar with GitHub and you'd like to leave feedback on there through issues and things, then please go ahead. I think the only other thing I wanted to say is that you can open these exercises as a Jupyter notebook directly. So you might have used Colab or Binder. Let's click on both. So certainly the PyMatGen example you can do in Colab, but this just gives you a slightly different way of reading them. And I think you've already used Jupyter notebooks throughout this course. Well, I know you have. So this hopefully should be kind of familiar, this kind of interface to you. So you could add a cell, for example, at the bottom of each exercise and start doing some Python here. So probably won't work, but okay. So you're being warned that I'm not as trustworthy as Google, apparently. I don't believe that, but you can run the actual code if you click run anyway. And eventually, once some computer somewhere in the world has done its thing, it will initialize a Python kernel for you, which will run the code you've asked for. So at the bottom here, we have this example code, which you can just run. So you'll see, I won't go into this right now because you can go through this on your own time, but we're just going to pick a particular Optimade base URL. We're going to add a query to it. In this case, we're looking for anything that has carbon, silicon, germanium, tin, or lead. We're going to get the response in Python, and we're going to print the first result. And you'll see that it's basically the same stuff I've just gone through in the browser. So do have a look at that. And if you need, for example, if you need a Google account for Colab, I think you probably do. You can also just use the Binder link, which is a very similar interface. Looks more like a standard Jupyter notebook. I think it's actually what I prefer. And you'll see I can run this without any issue with a Google account or anything. Okay. Some links on the slides as well. I imagine you'll get access to the slides as well as the recording. So you can just click on these links. Same acknowledgements as Gian-Marco, I guess. So acknowledging all the databases, some of the people that wrote the specification, some of the names on the paper, and finally, thank you all for listening. And look forward to working with you over the next few weeks.
Thank you very much, Matthew.
Let's leave that slide up. So yeah, any questions now, or you can either sort of leave it to Friday or till after Marcus's talk. I guess we went through quite a lot there, so it might be quite a lot to take in until you've actually done the exercises. But
there's some digesting.
Yeah. Okay, great. Works for me.
Thank you very much, Matthew.
Thank you very much.
No problem.
Or maybe,
thank you very much.
Yeah, Marcus, maybe you can start sharing your screen unless there's questions. Yeah, go ahead, Marcus.
Okay, you should see my screen now.
Yeah, you do.
Yes.
And before I start, Gian-Marco, can you remind me how much time do I have until?
You have plenty of time.
Until noon. Okay, I just take my time then. Okay. Yeah, thank you very much for having me here. Also, thank you very much to Gian-Marco and Matthew for the already provided content, and I tried to pick up on a few of these themes that we just heard about. Yes, my name is Marco Scheidkin. I'm from the Nomad project. I'm with the Nomad project for almost 4 years now. I'm basically the lead developer, the IT, the tech guy that is responsible for most of the operation and development things. Yeah, Nomad is like a bigger project. We are hosted in Berlin at Claudia Draxis Group, but yeah, originally Nomad was an European EU-funded project with lots of participants all over Europe. Yeah, contributing to it. Yeah. Let me go a little bit through the stuff that I want to talk about. Again, in the previous talks, we already heard about Optimade and what it is, and also about how the internet and APIs work in general. And I'm now here to talk about the specifics of Nomad. So I have to, while Gian-Marco and Matthew were like emphasizing the commonalities that Optimade provides, right, throughout all the different databases, I have to be a little bit the bad guy and focus on the specificities, right? Like ideally, you would ask yourself, why do we need to talk about Optimade and Nomad when Optimade is the same for everything? But of course, all these databases have their specific features or the specific types of data they want to provide that are not yet covered by Optimade by all means. But Optimade has features for this, right? In Optimade, we have the possibility to also have provider-specific things, specific properties that not all the databases support. And I want to talk a little bit about this, how you can use Optimade to get the provider-specific properties, and give a few examples what this means in terms of Nomad. And I also want to pick up on Matthew's ideas about how APIs work in general, and maybe give you a few more ideas how the internet works and how APIs work by going through more examples. And there are also some common things in there that are not super Nomad specific that can be applied to all kind of API work. But before I start to go into Optimade, I also want to take some time to talk about Nomad itself, which might also be interesting to you, just to see what Nomad is as a database, what its focus is, and how you might use Nomad even without Optimade. Okay, so let me start with the Nomad part. I think it will take about maybe 20 minutes, half an hour. And then I go into the Optimade specific part where we also will see some demonstrations and how to actually do things for the other half hour of the talk. Yeah, the slides that I have here and all the links that are necessary. Yeah, I guess we will offer this for download by some means. If you want to follow everything in here, you can do this afterwards. Okay, what is Nomad? You already heard there are lots of databases out there. So what is Nomad's angle? And what Nomad is, in our point of view, is a data sharing platform, a data management platform for material science. And this has like two things in it. One is that it is about data sharing and data publishing. So this is like in contrast to many of the other databases that you will see. We try to be, we are not hosting our own data, right? We are not a high-throughput database that is calculating data themselves. We are basically hosting the data of others. So the idea is like, if you are a researcher in material science and you have some data to share, you can use the Nomad service to publish your data, reference your data in publications and papers and stuff like this, and basically treat Nomad as a publishing outlet for your material science data. That's one part of it. And the other part of it is the material science part. And this is that Nomad wants to differentiate itself from more generic services like Zenodo, for example, where you can publish arbitrary data. Nomad is really specific for material science. And that means that when you give us data, we try to analyze it. We try to find the specific crystals in it. We try to find specific properties in it and offer them with an interface and an API that makes it possible to search for these specifics. Here in the background, you see a few screenshots from our search interface and also like an overview page. This is basically what we show for all the entries that we have in our database. Later on, we will see some demonstration of this, and I click around in the GUI a little bit. This is just for a first impression. It's a typical thing, right? You have a search interface, typically with a periodic table, and then you can start making your queries and your filters. And then we have some visualizations of all the data. We also have like something that we call the Nomad archive. I will talk about this in a minute, which is like a common data format, a common scheme that we apply to all our data. And then there's also the possibility to analyze the data with Python notebooks. I think in the overall program later this year, or maybe in the beginning of the year, there will also be some talks about the Nomad artificial intelligence toolkit in particular, which allows you to run Python notebooks directly on Nomad data. And of course, we offer people the possibility to upload their data. So there's an upload part of our app where you can provide your data. I will also have like a few more slides on this to tell you a little bit about the publishing process and how you can provide your own data to Nomad. So the general idea of Nomad is really to assist the research process by allowing people to share their data and to publish their data. And the overall idea is that you typically research scientists, they have some data on their hard drive and they do simulations, when they do experiments or whatever. They produce data and we basically want to offer them the possibility to upload their data and then to publish their data so that others can explore the data. That's another part of our functionality. We want to allow people to look at the data, explore the data space, analyze the data. And then the idea, of course, is that the cycle closes and your analysis and exploration on Nomad gives you ideas for future research, and then you start the cycle again. In particular, it's like, I think it's comparable what you do with paper publishing, but now this is about data publishing, which is like a big important factor in the future, as we feel, because when we want to make our data reproducible, providing the data is like a very important part of that, right? Another idea that we follow with Nomad is that we also offer our software for local operations. So if you want, you can take the Nomad software and run your own Nomad. This is what we call the Nomad Oasis. And the idea behind this is that typically you have this use case that within your institute, within your group, you have PhD students and people come and go, right? And they all produce data, and typically it's like often lost on old people's computers, and then you ask yourself, the PhD student that just left us, he had some data, but I don't know where to find it, and all these kind of things. And to help with this situation, for example, you could also use Nomad, install it locally at your institutes, and then ask your employees to please use our local Nomad to manage your data, and then it never gets lost again, right? So we introduced like a shorter circuit in this whole data managing scheme here, and allow people to upload data locally, and then you can use the platform and use all the exploration and analysis functions to work with your data locally, and still have the possibility at some point to decide, okay, now my local data is ready for publication, and I want to put it on the central installation of Nomad where everybody can find it. This slide here, I try to compare Nomad a little bit to other projects that we have, right? You already heard there are lots of databases out there, but there are also lots of other products that are somewhat related out there. And I hope that this helps a little bit to locate what Nomad actually is, and also clarifies a little bit what the other projects are about, and how they might be connected. So on this landscape here, I try to put those things that are like similar, closer to each other, and things that are more different, farther away from each other. And if you look at this, let me try to point out a few examples here. For example, we heard about the high throughput databases like the Materials Project or Rflow or OQMD, or also the COD database. This is what I would, without meaning it in a bad way, what I would consider like closed databases, right? They are basically hosting the data that they provide. And in contrast to this, projects like Nomad want to be like open databases, right? We want to be publishing outlets for others. We want to allow other researchers to post our data, their data to our database. And then if you ask yourself, what are these databases actually hosting? It's basically data that's produced by something, right? We have all these ab initio and electronic structure codes, for example, or molecular dynamic codes, or more things like this that are basically our data acquisition tools that are providing all the raw data that are then used in high throughput, or that are then published on databases like Nomad, for example. Another broad categories is everything around workflows, right? Where we have like low-level workflow engines like Fireworks, or something that is more material specific like ASE or Pymagen, right? Or we have platforms like AIDA, which I think you will hear later in this week about, where you have a workflow system that is then also connected to the possibility to publish something in their materials cloud, which also provides you with the Optimade API implementation, which are more like Nomad, right? But what is different to Nomad is that they have their own workflow system that you can use to provide the data there, or to acquire data there. And then, of course, you have Optimade itself, which is more about making data fair, making data interoperable. And there are other initiatives in this direction as well, right? There are data formats, for example, in material science experiment. Nexus is such an example. Or we have all these semantic web technologies, and where it goes into the direction of ontologies, specifically for material science, for example, this European effort in creating a common ontology for all of material science. And then you have other projects. For example, Zenodo is one of those where you have a data publication service that also allows you to upload data and to publish the data, but that are very generic, right? Zenodo, for example, doesn't really care what you upload. You can like upload arbitrary data there, and then you can give some metadata, give your data a title and name the authors and give an abstract and stuff like this. Which is also a valid option, but we fear that in order to be useful in material science, it's really necessary to identify specific data using specific queries. And this is what a database like Nomad is all about. And this is also what Optimade is about, right? Really allowing these specific queries for crystal structures that allow you to pinpoint the exact data that you need, similar to what Gian-Marco showed in the beginning, right? A Google search where you can type in this kind of stuff is really useful to do all the screening and filtering processes. Yeah, though this is a little bit of course, there's lots of more projects that you could talk about, right? I just want to give this like little overview of how I see that this landscape of material science data looks like in terms of projects. Yeah, so as a short summary about Nomad, so we are basically a web service that you can use to upload your material science data. And then we basically allow others to explore your data, to download your data, to visualize the data and analyze the data. A little bit of history. I think the first Nomad service was created in 2014, which was the Nomad repository, which already allowed people back then to upload their raw computation input and output files. And by now we acquired about 11 million code runs. So we are basically counting the simulation runs that you were doing, and this overall all the raw data or the input and output files of these code runs that people uploaded or they came from other databases amount to over 100 terabytes of raw data. And then one key thing that Nomad does is we are trying to parse all the data and extract all kinds of properties and information from these raw files. And there you'll find over 10 billion individual data points in the Nomad database. We support over 40 different codes. These are mostly all the electronic structure codes and then some of the molecular dynamic codes. The data that we have comes from like over 400 users from all over the world. and from 3 large high-throughput databases from Rflow, OQMD, and the materials project. And we currently have about 250 daily users roughly that are visiting our website and using our services. I want to talk a little bit about how Nomad works, so that you get a better impression about how this publishing works and what does it mean. I provide data and then I see something. So the overall idea is always that we start on your hard drive and we assume that you are a material scientist and that you have run some electronic structure code simulations. Let's say you have used the VASP code to perform some computation, or you were using UpInit or whatever. And this usually gives you files, right? You specify a simulation input in files, and then you also get output in files. And what you can do, or what you have to do to publish this data on Nomad, is simply put everything into an archive, use zip or tar to create zip files or tar files, and then you can upload these files to Nomad. And what Nomad is then doing is basically extracts your tar file, and then we look at all the files and we try to discover files that we recognize. So for example, if you upload a VASP run XML, we would recognize it as something produced by VASP, and then we would apply our VASP parser to it. And then this parser would basically go through this file and try to identify all the different things that are in this file. So it would try to identify all the input parameters, the system that you have specified. It would try to identify the computation results that you have been doing. Let's say you performed the geometry optimization, and you would get the individual calculation outputs, the energies computed. If you configured VASP in a way that you wanted to compute the density of states, then you would get the density of states data, and so on and so forth. So our parsers basically try to take these vastly different files, right? If you look at a VASP output file and an UpInit output file and an output file from any other code, they look vastly different. Very often they are not even machine readable, they're just ASCII files, right, that report lots and lots of numbers. And in order to make them useful for your analysis, you have to parse them to at least by some method to get to the individual numbers. And this is what Nomad also does for you, right? Basically parsing everything and trying to capture all this information in a machine readable format that is then homogeneous across all these different codes. So similar to how Optimade tries to be an API or a common API for all the databases, what Nomad tries to do with these parsers is to provide a common interface to all the various formats that are out there. And yeah, and this the files that we're creating out of this we call the Nomad archive. So for each of the code runs that we identify, Nomad will create an archive, and in this archive you will find all the information about the use method, about the input parameters, about the system, and then also about the results. And then this archive and this common view on the data is then the basis for everything that you see in Nomad. This is then what we use to put in our search interface. This is what we use when we implement the Optimade API to provide these structures there. This is what we use in the Nomad encyclopedia, which is like a picture book for materials, where you can see like all the computations that go into a certain material, and then you can use visualizations to explore a little bit what this material and its properties are about. This is what we use in the analytics toolkit, where we try to apply machine learning to all this data to discover interesting properties, and so on and so forth. Besides the Optimade API, we have our own API to explore this data. Yeah, there are lots of different tools and services around it, and later on I will have a little demonstration to show you a little bit more about it. Yeah, but the important part is that that you understand that we are not just hosting your files. We are really trying to analyze your files, look into it, and provide all these important metadata that are then driving our search, our APIs, and hopefully also your analysis. Yes, I think that's what I wanted to say about how Nomad works. Maybe a few more words about the Nomad archive, which is basically our common data format. I already told you we use our parsers to extract this information from the files that are provided to us. And this archive format is machine readable and it is structured. So everything is basically structured into different sections, and the section structure is common across all the different codes and allows you to have like a common interface to all this data. So for example, we capture a code run in a section run. This is what you see here, right? So on the top level, we have like the section run, which contains everything that is within the code run. And then there might also be some workflow information, some additional metadata. And then within the code run, for example, we differentiate between the method, so everything that went into the calculation, and the system, and then the calculation results itself, so everything that came out of the calculation. And then, for example, if you look closer at the system, then you see, okay, for each of the systems, we provide you see a viewer here, and then we provide basically the atom labels, the atom positions, formulas, the letters, and stuff like this. And this is here our GUI for the archive, which allows you to explore this graphically in your browser, where we try to have like, I don't know, this more mathematical representation of the lattice vectors, for example, where you have units attached to everything and so on and so forth. But of course, this is our GUI, but all the data is also available through API, and you can download this data in machine readable form. You can get a JSON representation of this and then use this in your analysis scripts or do something with it. And maybe a few words more about data in general. The challenge that Nomad faces is that we, on one hand, we have like all these codes out there that produce different data formats. And Nomad now tries to unify these formats through parsing. We're basically translating information from the specific formats of the various codes into our generic format. And this includes basically two problems, which I have visualized here with symbols on the one hand and with different colors on the other hand. So the first obstacle that our parsers try to overcome is the different formats itself. That is basically how the data is represented within files. Like sometimes it's an ASCII file, sometimes it's an XML file, sometimes it's already a JSON file. Like you have all these different baseline formats that have to be parsed. That's one part of the equation, and the more challenging one is the other part, and this is the information itself, right? Using different file formats can also mean that there are just different types of information in there. So not all the codes are really producing the same things. There's a huge overlap, of course, because they are all about material science and they're all about crystal structures. So for example, all the codes have a similar understanding about what information needs to be presented to describe a crystal, like something like you have to describe the sites and the elements that you use at the various sites and what position these sites have, and you have some description of the lattice for the crystal. And these kind of things are common. But then there are also like specifics, right? All these different codes also specialize in certain things and provide different properties and so on and so forth. And this is where things can be vastly different from one code to another. So another challenge is also to integrate all these various types of data into each other. And this is what I want to represent here with the symbols. So when you look at something like Nomad or the Nomad archive, you always you only can see at first glance you only see the commonality. So what is the same across all these codes? Yeah, if you dig deeper into the archives, you will also find code-specific stuff. So things that are unique to certain codes. And the data is also in there, but you have to be aware that what we try to present here, combine here, is usually just the cross section of everything. And this is something, a problem that also applies to Optimade as an API. So Optimade is very good at providing functionality like a filter language and a common output format for crystal structures. But when it comes to representing individual properties, this is where there's a lot of work ahead of us, because this might be very different from method to method, from a type of data to a type of data. Okay, I think that is enough for theory. I will skip these and jump into demonstration mode. First, I want to show you a little bit what our graphical user interface looks like, and then we look into API work and how to use Optimade with Nomad. So this is what our web page basically looks like. We have this overview that roughly explains what Nomad is, which components it has, and so on and so forth. So most people skip this right away and they just jump into our search interface, because I think that's the more intuitive way to explore Nomad. So I get some yellow lines on my screen that I think are not drawn by me. But anyhow, let me, I don't know how to get rid of them. I don't know if you can see them. So I will just ignore them.
You can see them also.
So the yellow lines are not part of the interface, just ignore them there. I think they're drawn by some of the participants of this workshop. Yeah, so this is our search interface, and like most material science databases, right? You start with a periodic table, and then you can start to do filters. Let's say I'm interested in compounds that have titanium in it, and then maybe also have oxygen in it, right? And you see like the colors are changing here. Something is happening. And if you look at this number here, you can see that you basically, by applying these filters, you're reducing the amount of available data, right? So initially we start off with 12 million calculations, and now if I say, okay, I only want to have those that have titanium and oxygen in their formula, then I'm already reducing this work quite a bit, right? And this is very similar to what we saw with Optimade, right? These kind of queries that you want to do. Other aspects that might be interesting, but besides like looking at the element, is like other stuff about the crystal systems, for example. So you might be interested in, I don't know, just looking at ternary systems, or you only are interested in bulk crystals. And maybe you're interested in crystals that have a certain symmetry, and so on and so forth, right? This is like all kinds of filters that you can apply, and with each filter, you're basically funneling down the remaining sets of results. There are other filters that you can apply. So let me clear all those here. We have something about the use method. This is where you can select the code that was used to produce the results. You can filter for basis set for the used functional, or at least a rough classification of the used functional. And you can filter for the properties that were computed. So let's say you are interested, you want to see in electronic density of states, and you are interested in data that was performed with the WASP code, and then you were interested in like the, let's say the titanium oxides. So then you basically created like a practical filter that might actually be useful. And then if you scroll down, you see the remaining results. So they are all there are still 11,000 different simulation runs in there. And for example, here we see some provided by the materials project. And if I go here and look at the details, and you get this general overview about the calculation, where you can, you have this little browser to visualize the system here, and we see the density of states that we wanted to have in this browser here. And then if you scroll further down, you see, okay, here was a geo-optimization performed, and you get a little bit of a telemetry about this. On the other side, we have like the more general metadata, like what code was used, what functions were used, and so on and so forth. Yeah, and you also see again that this is from the materials project. Yeah, so that's the basic overview that we give. And then of course we allow people to download the raw data. This is what Nomad mostly is about, right? About data sharing. So you can see the WASP run file that this is based on, and then all the other files that were put up to Nomad alongside, like all the, I don't know, input file into DOSCA and the eigenvalues and so on and so forth. And then you can like select everything and download if you like. And we also allow the archive view on it. This is like the parse data, where our parsers has basically try to homogenize all the information within this vast file. And you can also use this to explore the data. So that's basically the in-depth version of all the past information. Like this was the overview, and now we can look at everything, and we see, yeah, for example, all the method parameters that went into it. Like again, maybe what are the functionals used, or what are the K points and so on. And then we also have the system information here. This is what we will later see is what we use in Optimade to, or for Optimade to provide all the functionality there, like the typical stuff, the atoms that go into the system, the lattice vectors, the atom positions, and so on and so forth. And then also we have the calculation results in here, and here you will also find the density of states, for example. And the good thing about the Nomad archive is that all this information is like in principle machine readable. Like all these different sections you can get as a JSON document. So if you want to analyze the or visualize it differently or whatever, you can basically download this as a JSON file, and then you get all these structured information and all the numbers behind it, and can then analyze it with like your Python scripts or whatever. I will later show how we can ask these kind of queries with Optimade and get to the archive files using the Optimade API as an example. Okay, though that would be my demonstration of the graphical user interface. I think you get an idea now how data in Nomad looks like. It always has these two components. It has the raw files that were uploaded, and then these parsed files that contain all the metadata and information in a machine readable form. And this is then also what we use to populate our implementation of the Optimade API. And this is like the next part of the talk. Let's jump into our implementation of the Optimade API and see if it's looking similar to what Matthew has presented about his database. You can reach the Optimade API through the provider's dashboard that Matthew showed you. You can also reach the Optimade API through our API overview page here. This is also where we list our own APIs, and here we also have the Optimade API. So let's go to the Optimade API here. This link basically gets you to this overview page that most of the implementations will show you, and of course there is also this dashboard that Matthew was talking about. That you can use to have an easier time working with the API. We show this in a minute, but first let's start with the all-important info endpoint just to see whether the API is, oh, that's bad. This is how far demonstrations go. Let me try to do this with the dashboard. There I know it works. So the info endpoint. So this is the dashboard. I don't even recall if Matthew had showed this. This is coming from the Optimade Python tools, which basically provides the baseline implementation for Optimade APIs, which we are also using, and which produces this online dashboard, which allows you to use the API directly in the browser without having to use like Python or curl right from the beginning. So that's a user-friendly introduction to APIs, I would say. And here we can also try the info endpoint. So let's see if it works here. And here we get all the info endpoint information about our implementation, which is like the usual stuff, right? A few links about what Nomad is and where it comes from, and the available endpoints that our API supports, and so on and so forth. Usually you just use this to see whether the API is there and what it supports. But there are more interesting endpoints, I would say, in the API that really help you to do some useful queries and get to some actual structures. And this is the structure endpoint.
Hello, Marcos.
Yeah.
Is this on Jupyter Notebook? Can we get it there?
This is not a Jupyter Notebook. This is.
I know. I'm asking if we have it on Jupyter Notebook.
I'm not really sure what you're referring to. So we will later see a Python example that you can use within your Jupyter Notebook if you want to. Otherwise, there is also like within our analytics toolkit, we have a few notebooks that also show how to use the Nomad API, for example. There's one tutorial on this where you can do this, where you will actually be able to open Jupyter notebooks on our servers. This is basically this part of the web page. But this is not what I'm focusing on in this talk, right? So that will be part of another talk, which is, I'm not sure, later this year or maybe in the beginning of the next year.
Okay.
Yeah.
Okay. I would like to ask, do you have any link to other databases, such as genome database or protein database? Do you have any link or any section concerning the working with like primer design, protein folding, or production of proteins, specific proteins?
So there are a few how do I put this? There are a few things that we try to provide. So one, for example, is, let me go back to the search results here. Let me try to reproduce what I just said before. Let's go to this materials project entry here, for example. Within the archive, you find a few things that might help you. One thing, for example, is that with each of the systems, we try to provide, let me see if something like this is in here. Sometimes you have from the Springer database about materials, you have some labels and references in there. In this particular example, we don't have them, unfortunately. This is also what you can use in our search, right? There is under system, these kind of things, the compound classifications, they come from the Springer database. So I think when I also filter for this one, then I will definitely find something that has it in it. So let me check this here. And then with this Springer database, you will usually find like reference papers and stuff like this. So this is information that comes from there. This is where you also then will find links to Springer and certain publications. Publications there. Another thing that we do, and that this really also depends on the entry, whether we have it or not, is this section prototype, I think, which provides the reference prototypes from the Aflo database, which might be another thing. And then it really depends on who provides the data to us, right? Sometimes they also give us references. Let's see if for example, no, in this case, but sometimes people put in references here when they say this data comes from a certain paper of mine or from a certain database of mine. For example, the materials projects, when they give us the data, for most of the data, they put a reference in here that goes back to their respective page. And so on and so forth. So it really depends on where the data comes from and what information the people give us, or what we can automatically detect from the data. I hope that answers the question to some degree.
Okay, thanks.
Okay. Let's go back to Optimade. And also Optimade has this links endpoint, right? I have to admit that Nomad doesn't really have a good implementation for this yet, but I know that some of the other databases do, that they provide links to typically within their own database, but in principle, I think this can be used to also provide links to other databases when there is some connection in the data that is relevant. This is, for example, something that Nomad should use, I guess, to provide these kind of things. We will probably do this at some point.
What I mean.
Yeah.
Yeah, that's what I mean.
Yeah. Okay. So we at the moment don't really implement this much, but this is what we could do in the future a little bit more. Yes. Okay, let's continue and let me jump into the structures endpoint and let's try to do similar queries like Matthew was doing them before. Oh, I already typed some in here. Yeah, so this is the structures endpoint, and as you saw, that there are multiple parameters that can go into the structures endpoint, and the most important one is the filter one, right? This is where you ask your queries using the Optimade query language, and this example query here, for example, allows you to ask for all the structures where the set of elements contains all of those, right? Where there are at least titanium and oxide among the elements of the system. And then you have this search button here, or this execute button that you can use to actually run the query. And then the dashboard will run the query for you. And then after a while, you will get the results below here. And then you can scroll through the results. So we typically have this data category, this data key, and then you have an array with all the result information in there. And for each of the returned objects, you see first the Optimade common properties, like the identifiers, and then you see here the elements that go into this particular system, and you see oxygen and titanium are indeed among them, and the element ratios and so on and so forth. I think Matthew already did a good job in talking through all of them. So let's scroll past them. And then you will see that there are also some specific properties. These are all those that start with this _NMD. So these are considered provider specific properties, and these might look different in all the different databases. So NMD stands for Nomad, and this is where we have our Nomad specific properties. And here we basically have some of the things that you see in our archives, we also put here into the Optimade implementation. So for example, everything that you saw in the search interface is then also here, like the symmetry on the crystal, for example, or the basis set that was used, and then the functionals that went into the simulation of this crystal, and there are lots more. And the key thing is that these are not just available here, but you can also use them in your filtering, right? So let's say the Nomad filters, the Optimade filters get you to a certain point, but now you want to be more specific. And let's say you're interested not just in titanium oxides, but you also want to say that these have been that you are interested in calculations where this has been computed with a certain code, for example, then you could do something like this. Where you say, okay, this specific property of Nomad that describes the name of the used simulation program should now be WASP. And then you can re-execute your query, and then you should also get results for this. But now the filter is more specific and more narrow, and will only provide you results that have been done with the WASP code, provided that you actually use the property in a correct way and did not made any mistakes in this. So I think one thing that I have to be careful about is spelling the end in capitals, and then I might have done this wrongly. And let me cheat a little bit and look at my slides here. It has to be like this. Well, I think I spelled it correctly. Well, let's try this again. Copy paste is always safer than trying to spell it out. Oh, but I copied the wrong thing. So, but it, okay, let's try again with the capital N and see if this works. Otherwise, like all technical implementations, also Nomad has its flaws, and stuff is not always working, unfortunately. Okay, then it was really the misspelling of the end. Now I get actual results. Yeah, the results now look the same, right? But the difference is that we now have a smaller set returned. Now we only have those calculations in there that have the code name WASP in it. Let's talk about a few more things that are specific, that are not specific, but that are more general to Optimade that Matthew maybe hasn't captured yet. Like what the dashboard also gives you is like this information about the URLs that were constructed from your query and how you can use this with curl on your command line, for example. And I want to highlight a little bit on these URLs here, right? So you can use the dashboard to create queries, but what you're basically doing is you're constructing URLs, right? So that you don't have to do it manually. But all the stuff that we entered here, let's say the query that we have here, eventually ends up in the URL. You see this here with the filter parameter, right? And then you see here our query. It looks a little bit scrambled, and this is because in order to be a proper URL, all the special characters have to be encoded, and this is what you see here. This is what the dashboard is doing automatically for you. It's replacing all these spaces and the upticks and whatnot with quotation characters. But in the end, this is like a regular URL that you can use everywhere in your browser, or that you can use with wget or curl or whatever. So for example, I can just copy this whole thing here and just put it in my browser to play with. And I think something similar is also what Matthew was using in his presentation. Depending on how you set up your browser, you then get a plugin or whatever that allows you to display the resulting JSON data a little bit nicer, where you can like fold everything and so on and so forth. Let's have another look at a few of these parameters here. So one is the filter parameter, which is like the important one where you ask a query, but then there are all these other default parameters that were filled out by the dashboard, for example, about the page offset and the page number. So one thing you quickly realize is that if you do a query like this, that you're only getting some results, right? And if you use look at the metadata section where it says what data is available. Like in general, Nomad has like these 12 million kind of calculations in there. And then this query returned like 2,000 of them, right? But they are not 12,000 within this answer. And this answer, there's only about 20, right? And this is what is set with one of these parameters here. Let me see. So after the filter, you have this page limit 20, right? Which this is telling the API that we are only interested in 20 results at a time. And then the question is, how do I get to the other 12,000? And this is where you can use the page offset, which allows you to specify like an offset to your query where you say, okay, I want to have the next 20, right? Or I want to have the 20 after the first 40, or I want to have the 20 after the first 60, and so on and so forth. This is how you can control the pagination of the results. And this is also a prime example for REST APIs, which are all doing this similarly. As Matthew mentioned, the whole idea about REST APIs is that the server can be stateless. So the server won't really remember where you are. You have to provide this piece of state to the server. This is where this representational state transfer comes from. We are basically transferring the state of our pagination to the server so that he does not need to remember the state, and we can tell it which page we want to look at. And to make this a little bit more convenient, you also have these links within the answers that show you the way to the next page, right? You see this link next here, which basically allows you to get to the next page. Here you see the page limit is also set to 20, but now the page offset is already set to 20 so that we can jump to the next page. Yeah, that's let's say a good example of how pagination works. There are different modes in Optimade that in principle apply. All these databases might use a different mode. This is what Nomad is doing with the next key here, and then this allows you to go through the whole data set. So let's imagine that you really want to have all the 12,000 results. You probably don't want to click through all of them. And that's the whole idea of an API. You want to use a computer script to actually use the API. And that should be the last part of my presentation here, where I want to just give a brief example of how you could do this with Python. So for now, we're just looking at dashboards and user interfaces and the browser. But eventually, you want to do this with a Python script and automate, use the API to automate tasks. And this is what a typical script could look like, where you try to ask a query and then paginate through all the results to get all the information out of the results. In this script, I use the request library. The request library is a very standard library. It's mostly pre-installed on most Python installations. Otherwise, you can just pip install it. The request library is an implementation of the HTTP protocol and allows you to do all these get and post requests that Matthew was talking about without needing to do them manually. So we import the request API library first. Then we have a few constants here. We set the base URL, like if you want to use Nomad, for example, you would use the Nomad base URL to the Optimade API here. And then we have this particular filter that we're interested in. That is the same example that I was using all the time, where we look for titanium oxides. This time, let's say we want to limit it to those that only contain titanium oxide. So we set the number of elements to 2. And then we are interested in vast populations. So that's the filter. And now how can we do this? So first we need some kind of loop, right? Because we want to ask multiple questions. We want to paginate through the whole result set. So I remember the offset here. Let's start with an offset of 0, and then we have this loop. That might not be the safest way to implement it. That's just the most straightforward and hopefully the easiest way to explain it. Of course, there are different ways of doing the loop and whatnot. The next thing I'm doing here is I'm preparing a dictionary of parameters that go into the request. The first parameter that goes into the request is the filter, which is this one, right? And then the page limit. So let's say we want to get 10 at a time, and the page offset, and this depends on our variable here that we keep. So we start with 0, and then when we continue the loop, we will gradually increase this. And then let's say we want to have a certain set of response fields. I haven't talked about this yet, but when we were executing the examples before, we were always getting like lots of different fields for each of these entries. When you want to limit this to certain fields, you can use the response fields parameter. So let's say you're interested in the Nomad archive URLs because maybe you want to download all the archives for these 12,000 entries. Then you would look for for this particular field here. And then we do the actual API call. We use the request library to formulate an HTTP GET. This is what you do with this GET function here. And then we have to give the URL of the endpoint. So that's the combination of our base URL. And then we are interested in the structures endpoint, right? Then remember, this is the endpoint where you can ask the queries and get the individual structures from. And then we pass in all these parameters. And the beauty about this request library or using a library in general, that we don't need to do all the manual work, right? We don't need to encode the parameters, for example. This will be done by the library. So we don't really have to care. We can just prepare the parameters in this way and just put them in there. And then the request library will initiate the actual HTTP communication. So it will open a connection to the Nomad server. It will send the GET request, and then it will receive the answer. And then once it's finished, we can consume the answer in form of a JSON document. So we say JSON here. And what this gives us is it basically interprets the result as JSON, already parses the JSON, and we get, we get a Python object here, which is already a dictionary where everything is parsed, and we can then just consume this as we typically would do with a Python dictionary. So if you remember the responses from before, the top level dictionary always has the key data in it, and behind the key data we have the list of results. So we go through all the results that are behind this data key. And then for each of the results, we're interested in the attributes. And here, let's say we want to print in Nomad archive URL, which you remember is the one that we requested here in the response fields. So this will then basically print all the Nomad archive URLs that are in the response. And in the first response, we expect to have 10 results, right? We use the page limit of 10, so we will only get 10 results, and this is what we are printing here. And then now the question is, how do we get to the next response? And this is where we then now increase our offset here. So we go we take the page limit and add it here to the offset so that the next time we get we get the 10 results after the first 10 results. And then, of course, at some point, we also have to stop our loop. So let's say we look at the data returned, like the principal available data for our query, and look whether we have exhausted this one, then we break, or let's say we stop after the first 100. Of course, you can also run this through all the 12,000. Yeah, so you can formulate like different stop criteria depending on what you actually want to do. And then if you run a script like this, what's supposed to happen is it goes through the loop again and again and does all these requests by gradually increasing the page offset. And this basically allows you to get a large number of results automatically without having to click or go through everything or whatever. So let's say you wanted to download all the archives. Instead of a print, you could use the request library again to take this URL that you get here and then maybe get the archive information from Nomad as well. And then, I don't know, save it to disk or do something with it. This then really depends on what type of analysis you want to do with the data. I just wanted to, yeah, briefly show you like how you would treat an API using Python in general. I hope that this gives you like an introductory example on how to use the request library to talk to web servers and to talk to APIs. Okay, so let me stop here. So yeah, what we saw in this presentation is, yeah, I try to continue what Gian-Marco and Matthew started and talk a little bit about how to use Optimade in the specific context of Nomad. We talked a little bit about what Nomad is, and then I showed you a few more parameters on the Optimade API. We looked at Nomad specific properties and how you could use them. And I showed you this brief example of a Python script that you can use to actually talk to an API. And even though this example was for the Nomad database, you can adopt the script for other databases as well.
Marcos.
Yes.
How can we get that Python script?
I don't know. You mean how you get this particular Python script?
Yeah.
Yes. I think we will share the slides afterwards, or provide URLs so that you can get to the slides, and then you can copy paste this to somewhere.
Oh,
if I could just say, Marcus, so I'm actually adding your snippet here as an example at the bottom of the exercises. So if people go to the GitHub repository that I linked to,
okay, great.
You should also be able to find this at the bottom.
So then you will also find this in the repository with all the exercises in it.
Okay, okay, thank you.
But of course, it's a better lesson when you try to implement this yourself, right? I mean, copy pasting it, running it is one thing. You learn more if you actually try to come up with your own example and maybe just use the information and then try to implement it yourself, which will also give you a great exercise in dealing with all the errors, right? Typically, if you take an example like this, you just run it and it works and then you're fine. But the fun part is when you try it yourself and you make mistakes and then you have to deal with the errors. This is, I guess, is the actual teaching behind this. And how do you deal with all the errors that come up and so on and so forth.
All right, we tried.
Okay, thank you.
I have a question, please.
Mm-hmm. Mm-hmm.
Okay, so I've been able to see what about data collection from the various things you have on the platform. But I want to ask, the first question is the database only related to material science? You know, that's the first question. The second question I want to ask is about my field is computational chemistry, and then what we do basically is that we use Gauss view to be able to model reactions like structures, and then we use Gaussian package to run the program, and of course we get the coordinates or Cartesian, you know, the values as input, and then we take it to the software Gaussian, and then we run it, and then at the end of the day it brings out the structure, which from there we can get our output. We can get some thermodynamic parameters such as the Gibbs free energy, the enthalpy change and all that. And then from there we can make use of the data, the total electronic energy, and then use that for subsequent calculations. So, but I want to ask if that is viable, like that can be used on your platform, like, you know, I don't know, is that applicable to storing of information because I don't know how that such information can be stored on your on this platform that is created. I don't know. Do you understand my question?
Yeah, I think I understand your question, and it's a very good question, because it touches on the whole problems of having workflows, right? So what you're describing to me sounds like you're doing individual calculations to get to a certain piece of information, but the actual thing that you're doing is you're then combining these individual calculations to get to a certain property or a certain outcome. So as I understand your question is how you can have like multiple of these calculations combined and describe the final result of your work. And this is where we are currently putting work into and try to improve the situation. But this is difficult, right? Capturing workflows means, in essence, that we have to capture a little bit a specific thing that you are doing without knowing about it. There are certain workflow engines that you can use, and if you use those, we have like an easier time in actually identifying the workflow that you used and making sense of the results. For example, if you use ASE or something like this, a platform like Nomad could in principle do something. This is, for example, what AIDA specializes in, right? You can use the AIDA workflows to really formally describe your workflow, run your workflow, and then you have all the data about your workflow available. We might in the future also provide the possibility to do this manually, to basically say, okay, I have like 1,000 Gaussians here, and the idea behind this was this and that, and I combine them in these and these steps, and this is the final property that I want to have. But this is something where we are still working on. But in general, the topic of workflows is rather difficult because it's like each workflow is different, and then the data that you need to describe each workflow is also different. What we have in Nomad is like lots of Gaussian calculations, right? But they are mostly disconnected. They're just there. Let's assume you have done some research and you have done a work based on Gaussian. What you can do is you can still upload all the Gaussian calculations, and then we allow to create these data sets here. Here you see an example. You can combine multiple combination into a data set. You can give your data set a name. And then you can use these comments, for example, to describe a little bit what you were doing within your data set. The data set is also then what you can use to reference your work. You can create a DOI for your data set, put it in your paper, and then you could also backlink your paper using this reference field here, for example. So this is the kind of information that you can provide, right? You upload all your raw data, write a paper about it, and then put in the information here, and this gives people a chance to understand what you were doing with all these different Gaussian calculations. Does the answer give some satisfaction? I'm not sure.
Okay, all right.
So I don't know, I could check the chat. Or otherwise, if there are no more questions, I thank you again for listening to this. And I guess Gian-Marco maybe has a few closing words for us.
So Gian-Marco had to slip away, I think, unfortunately.
Okay.
Nothing to do with your talk, of course. He had another engagement. So I mean, well, I guess I can. Well, so
yeah.
Bright for a second there.
Thank you very much.
Yeah. So thanks everyone. I guess we'll hopefully see you all on the Friday Q&As and the following talks as they come along. And as I said, so Gian-Marco has left his email address in the chat. So feel free to email him with any other questions. And I think I'll just leave the link to the exercises in the chat as well. Hopefully you'll be sent all of the slides from today shortly. So thank you, everyone. See you around.
Yeah, thank you very much. Yeah, bye.
And thank you, Marcus, as well.
Thank you very much.
Yeah, thank you, Matthew, for your thank you.
Yeah. I've added your snippet. It also runs, so that's even better.
Okay, you tested it already.
Yeah.
Okay, yeah, good to know.
Well, it runs on Nomad at least.
Yeah. So I will also put my slides in the chat. If I can do that, it chat disabled. I think I can't do this.
Yeah, I think I emailed one to Gian-Marco and he's going to send them out to everyone else.
Okay.
So if you just send it to him.
Okay.
I should stop recording, shouldn't I? Okay.